Hi teacher, Amanda here. I'm from class PE03, index number 1. And today I'll be showing you my circuit on preamplifier fabrication and testing. So this is my circuit. It is currently connected to a dual power supply at 9 volt, the function generator and the oscilloscope. And for my channel 1, it is connected to the function generator and the input of my circuit. It is at 1 kHz and 200 mV peak to peak. And channel 2 is connected to the oscilloscope and the output of the circuit. As you can see, when the input frequency is 1 kHz, 200 mV peak to peak, the output voltage is around 3.36 volt to 3.44 volt, which is very similar to my lab results of 3.44 volt. Now, we're going to test when the input frequency is 20 Hz, 200 mV peak to peak. We are expecting 3.36 volt. From my previous test lab results. And now it shows that my results are correct. It's at 3.36 volt. And we both got sine wave. Yes, now we are going to test when the frequency is 2000 Hz and 200 mV peak to peak. So we are expecting 2.24 volt from my previous lab results. Yes, 2.24 volt. And now on the oscilloscope, it shows that my results are correct. It's at 2.24 volt. At 2000 Hz. So now we're done. We're moving on to the semi-long graph. Okay, so at 20 Hz, the voltage gain is 24.51 decibel. Yeah, after my calculation, I plot the graph. It's at 24.51 decibel. And at 1000 Hz, the voltage gain is 24.71 decibel. And at 2000 decibel, the voltage gain is 20.98 decibel. So I calculate the voltage gain using my test results and I plotted them. So now we're going to find the bandwidth. The highest voltage gain in this case is 27.16 decibel at 100 Hz. So 27.16 decibel minus 3 decibel is 24.16 decibel, and that is the passband gain. And so to find the first frequency, we draw a line at 24.16 volt, and where the 2 points touches the graph, that is the bandwidth. So we find the 2 points and we find the difference, which is 1240 Hz, and that is the bandwidth. So, and that will be all for this lab, and please continue to watch the next video. Thank you. So So this video I'll be testing from test point 2 to test point 3, testing whether the potentiometer is working. For channel 1 is connected to test point 2, and for channel 2 is connected to test point 3. And now you can see there's a square waveform. So if the potentiometer is working, it should be able to trim my output waveform to a sine wave. It's able to act as a variable resistor, increasing the resistance to trim the output voltage. So now I'm turning the potentiometer. You can observe that the square wave is slowly turning into a sine wave. So it shows my potentiometer is working fine. So now I'll be testing test point 3 to test point 4. The frequency is set to 1 kHz like the previous lab. And channel 1 is connected to test point 3 while channel 2 is connected to test point 4. And here you were able to observe that the output waveform is the inverted version of the input waveform. The output voltage is the same as the input voltage. So now I'll be testing test point 4 to test point 5. We'll be testing whether the amplifier, which is another potentiometer, is working or not. So in channel 1 we have test point 4 and channel 2 we have test point 5. Currently the V in is 5.2 volts and the V out is 3.87 volts. Now I'm going to turn the potentiometer to check on whether is it working and will the voltage be amplified. So now I'm turning the potentiometer. As you can see, the voltage is amplified and the waveform changed from a sine wave to a square wave. So now the V out has become 8 volts after amplifying, and this shows that my amplifier is working. Here I'm just showing my initial value of V in and V out. Here I'm testing test point 1 to 5, and here I'm just showing that overall my circuit work and my output voltage is amplified into square wave. This is my circuit and all the connections are working. This will be the end of my video. Thank you for watching.